Listen to a slope of 0. Now listen to a slope of 1. The purpose of the video is to see if you can predict what these slopes are going to sound like. Welcome to mathandstuff.com. The purpose of this video is to show the use of one web page. At the bottom of the home page is the link to the videos. In the videos under high school and college, we're going to slope song. This is the meat of what we're going to do today. If you don't know what a graph is, or don't know what the coordinate plane is, play with it before you use this page. According to history, Descartes and Fermat developed the coordinate plane. Descartes was a sickly child, looked up at the ceiling, mapped the progress of a fly, and created the coordinate plane based on the tiles in the ceiling. Urban legend has it that Descartes looked out the window at the mountains. The word for mountain begins with M in French as it does in English. So, urban legend says the symbol for slope is M. This webpage, it's designed to introduce slope from the mountain point of view and from sound. Listen to a slope of 0. Again. Now listen to a slope of 1. You can see a difference. You can hear a difference. Slope is a measurement. The symbol is M, and here are some numbers that you should be familiar with. Again, a slope of 0. Again, a slope of 1. Now consider, what's the difference between them? How about what should a slope of -1 sound like? Before going on, before experimenting with the sounds, just sit a little while, look at this video, at this image, freeze your video, and see what you can glean mathematically from this picture. Before we continue, you might wish to look at the PDF file, the last pages of it. This is gone over in detail. I will do that now in the video, but that's not the purpose of the video. The purpose of the video is to see if you can predict what these slopes are going to sound like. That's where we're headed. This is the detour we take. The first slope we looked at was a slope of 0. Here's a line with a slope of 0. If we look at slope as rise over run, there is no rise. the rise is 0. But there is a run. If we look at a line of slope 1, it rises and runs. So if I start at 0, 0, I rise 1, I run 1, I have a point on that line. Its slope is 1. Its rise is 1. Its run is 1. Let's do it a different way. Let's start out with this point. Our fraction is equal to 1. Let's rise 3. 1, 2, 3, and run. 1, 2, 3. 3 over 3 is still 1. So a slope of 0 is completely flat. A slope of 1 has an equal rise and run. A slope of -1. If I start at 0, 0, in order to rise, I have to fall. So it's a fall of 1, and it's a run of 1. This is 1, that's -1. The rise is -1. The run is 1. The rise could be -3, and the run would be 3. It's still equal to -1. So we have a rise, which in this case is a drop, and it's the opposite of the run. The last and most difficult one, perhaps, to understand is the slope of a vertical line. If slope is rise over run, it continues to rise. You could say it rises 10, 20, 15. Let's put in a 10. Let's put in a 15. Let's put in a 1. Let's put in 100. It could rise 15, it could rise 10, it could rise 1, it could rise 100, but there is no run. So the run is 0. Division by 0 is undefined, therefore there's no slope, and the slope is undefined, or no slope. If you consider a few more slopes, let's look at this one. Pick a point. Find another point on the line. Rise is 2, run is 5. That's a slope of 2/5. If instead the rise is -2 and the run is 5, And that's consistent with the way the slope of 1 and the slope of -1 worked. The same would be true with a slope of 3/4. We're going to rise. Here, let's go. 1, 2, 3, 4. Rise 4. Run 1, 2, 3. Slope of 4/3. This slope isn't quite as large as 1. This slope rises 1, 2, 3, runs 1, 2, 3, 4. This one's steeper than 1. This one's not as steep as 1. Now, those are typical slopes you look at in math. In the real world, slopes are usually much less than 1. The slope of a handicapped ramp for wheelchairs, scooters, walkers is 1 to 12, 1/12. In the home, it's 1/4. The steepest road in the United States is in California, and it's 13/50. So you see that these real world examples of slope are much smaller than the one we used as a unit. Roller coasters, these are drop down. So instead of rising, roads rise and fall. Instead of rising, these are represented here as falling. We're going to start them both up at 200 feet. And on a normal roller coaster, you drop 8 and run 5. On the world's steepest roller coaster, which is found in Busch Gardens in Tampa, Florida, the rise is a drop of 200 feet, and it's 1 foot. So as soon as you start the ride, you fall. That's why it looks like a vertical line. This is almost no slope. If we moved nothing, it would be an undefined. Back to our page. A slope of 0 again. A slope of 1 again. For a slope of 2, how should 2 sound relative to 1? Reaches higher. Here we have at 2 units of time, the slope of 1 is up 2 units. Here on the 2, we have 2 units in time. The slope is, the point is now at 4. Play with this. That's the whole purpose of the video. I'm going to continue with more information. You should be able to figure out what the slope of these are. We did them just a moment ago. I still want to clarify and give you a few more examples. This is the definition of slope taught usually in Algebra 1 and used through calculus, all important. I'd like to look at a few more uses of slope in looking at functions. Again, the originators of the coordinate plane, Descartes and Fermat. And here's only one function. Now you got to think about mountains again. Good old Descartes and his mountains. If you look at this as the geography out a window, then if you're approaching and walking this path from left to right, you're going down a hill. The slope is negative. If you get to this point, you're at the bottom of the valley. It's a fairly steep valley cut. And if you go, the slope here would be 0, flat in the bottom of the valley. And then you continue, the slope is positive. You really can't get much more of a value for the slope than the negative, the 0, or the positive. If you look at the same curve, but use a tool that is made originally for use with your hands, a manipulative. There's a whole book on how to do it. There's a page in the book on how to use a slope meter. This is the same picture you used to study slope. This manipulative is digital, and it's harder to work on digital, but it's easier to work with your hands. The masters are all in the book. I'm going to pick up the point and the arm, and I'm going to attempt to pick up the background, and I'm going to see if I can move it. No, I can't move it all. All right, so let's put the arm there. Let's pick up the background. Let's try and place it. Now, we now have a tool to measure slope. Well, you have to take the arm and make it tangent to your curve. Tangent means it only touches in one spot. A tangent is a line that only touches a circle or a curve at one spot. These two circles are tangent. It is a trig function. It is important. It's a word you should know. Let's try a point. Let's say over there. Let's put the arm here. Let's move the background. And if we try and make the arm tangent to the green curve, that's about what our slope is. Judging by the numbers, maybe this is probably a -1.5. So drop 1.5, run 1. It's a slope of about -1.5. If I'm reading it right. Oh, we want the purple. At 1. That's about the closest we can get. Using this tool, it works better when it's larger and in your hands. But you can see by this that the important piece is the arm that is tangent. And this is a tangent to the curve. You can move your point on the curve, and it's stating for you the slope. So the slope at this point is negative, about -3. If we move it over more, that's about as close as I can get to 0. And then we go positive. Well, that's a parabola. It's a second degree. It's sometimes taught in Algebra 1, usually taught in Algebra 2. Let's go on to a little more sophisticated curve. Again, slope is increasing. Here it's 21.8, but the curvature is getting flatter. So the slope is decreasing. We get to a slope of 0. Now we go negative slopes. We go to 0. We go positive slope. It's getting steeper and steeper and steeper and steeper and steeper. Here we're already up to a steepness of a slope of almost 56. There are even more sophisticated functions. This one's a cubic. This one's it looks like a 1, 2, 3, 4, 5, 6 degree polynomial. A lot more fancy, a lot more curves. But you get the idea of what the slope is doing. And here it's 10, positive, about the same. Here we go. It's slower, steep, less steep now. And around here, we go into the 0. That's about the best I can do. One more picture. This is called a rational function, as in ratio, as in fraction. And here we have a vertical asymptote here and a vertical asymptote here, because you're not allowed to divide by 0. And if x were equal to 3, as it is here, if I put in a 3 right there, 3 minus 3 is 0. I get an undefined. But the slope here, notice the slope. Now it's 0. Now it's increasing, 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 increasing. Oh, it's getting steeper. The closer I get to the asymptote, the steeper the curve goes, the steeper the slope. If I were able to go to this line, its slope would be undefined. I cannot do that. I cannot do anything but approach it. We go back to the web page. The last item that's on the web page is computing a slope by definition as rise over run. Let's look at rise. Rise is the difference in height between where you start and where you end. Here the height is whatever it is. What is it? 2. And here the height is, looks like about 9, between 2 and 9. Let's start out with this point. This point is, looks like about 1, 2, 3, about 3, 2. And the page does the computation for you. 3, 2 is the first point. And the second point is 1, 2, 3, 4, 5, 6, 7, and it's up to 9. And the page will compute the slope for you. Here we put in the wrong number. 7, 9. There you go. 1 3/4. Let's do it one last time with the slope meter. This is also downloadable. Here we're looking at where you're headed in mathematics. I just want to give you one more opportunity to create your own lines. If you look at this, you can tell it's definitely a negative slope. You rise -1, you run 1, 2, 3, 4, 5. So if you start out with B at -2, 5, and run to A, which is 3, 4, that's the slope you'll get. You can change your A and B. Let's change B. Let's change B. Let's make it -2 is good. Let's make it 0 here. It drew the line for you now. Here's the 2. Here's A. We rise 1, 2, 3, 4. We run 1, 2, 3, 4, 5. 0.8, 4/5. You've now played with the entire page. If you want to know how the page was built, read this. The important thing to know is slope is rise over run.